Hello, here we'll continue looking at least square approximations, and we will do two for the same data. We'll do linear and quadratic. Let's imagine the data. Again, 4 points at -1, 0, 1, and 2. The values will be 2, 0, 0 again, and 1. So that is this mysterious function we are trying to approximate, and we'll have two answers, linear and quadratic. And linear is what we did last time. So linear template is a plus bx, and fitting the data, we have a system with the matrix first column is all ones. These are coefficients for A, and then coefficients for B will be x values we substitute. And that is the matrix of the left-hand side of the system, and on the right we will have the answers given to us, this f of x values. So that is the system we are trying to solve. A times a vector of unknowns matching with B, and it is unsolvable on the nose, but we replace it by a least square system, which will have that matrix for the bulk and that column for the right hand side. So let's compute the matrix for the bulk and the matrix for the right hand side. So here's A. A transpose times A will be the product of 1, 1, 1, 1, negative 1, 0, 1, 2. I shouldn't be writing it because we computed it in general form last time. The answer will be the sum of ones as many as coordinates, which is 4. In this sort of skew diagonal, there will be the sum of x's, and in our data the sum of x's is 2. And then here we'll have the sum of x's squared, and that will be 1 plus 1 plus 4, 6. The column on the right side of the least square system, this is called least squares system. On the least square system, the first coordinate is the sum of b coordinates, which is 3, and the second coordinate is the sum of products of x coordinates, this column, and b coordinates, this column. So the sum of products will be -2, 0, 0, +2, summing to 0. And the least square system, written in the matrix form, ready for Gauss elimination, will be looking like that. So what we can do, we can swap the rows and half the first row. But yeah, okay, we can do it later. Let's just first swap the two rows we have, and then eliminate the second entry in the first column. And half at the same time row 1. And then here we're subtracting twice that, we're getting 0, twice that out of this, we're getting -10, and we still have 3. So yeah, we could do again elimination in here. We have to do it, making 10 copies of row 1 in place of it, and then adding row 2 to it, and at the same time changing the sign of row 2. So it will become looking like that. And in this row we'll have 10 and then 30 without, sorry, adding 3 copies. 30 without 30, 0 as desired, and then 0 times 10 is still 0, plus 3, and that will be 9. So these are the answers for A and B. A is 9 over 10. Our linear function will look like this, and then B coefficient is 3 over 10. And the values of this line, so maybe I should plot somewhere the points and draw the line eventually. So we have value 0 at 0, value 0 at 1. At negative 1 we have value 2, which is here, and then at positive 2 we have value 1, which is here. So what is the line? Let's compute all its values, and that will be enough to plot. 2 of them will be enough to plot. So at negative 1 we have 9 over 10 plus 3 over 10. We have 12 over 10, which is better known as 6 over 5, but whatever. At 0 we have 9 over 10. At 1 we have 6 over 10. Again, can be simplified, but I'm just keeping 10 as a common denominator. And then at 2 we have 3 over 10. Linear dependent. And we can look at, say, 9 over 10 here, which is really close to 1, and then 3 over 10, the value at this x value, so that will be line going like that. And then the sum of squares of these deviations, minimizing it for all linear functions. So let's compute what it is. It's the sum of squares of differences of entries in these two columns. So it will be 2, which is 20 over 10, and 12 over 10, which is the same as 8 over 10 squared. So sign is no importance. Then 9 over 10 squared, 6 over 10 squared, and then 10 over 10 and 3 over 10, which is the deviation by 7/10 squared. So all that over 100, making it over 100, we will have 6 squared plus 7 squared plus 8 squared plus 9 squared. And the sum is 230. So after cancellation, we'll have 23 over 10 as the deviation. And that is it. So that is our least square linear approximation. But we can do better if we allow ourselves to use not just linear terms in the approximation function, but quadratic terms. So that will be this quadratic least squares approximation, where the function will have more relaxed template. But the price for that is that now we have 3 unknowns to determine, and the system for determining them is still the same data we are given. The values at x points are to be equal to the values given. So let's write the system. We will have again the system will have a plus, or rather minus b for the x value -1 plus c being 2. Then at 0 we just have a being 0. At 1 we have the sum of a, b, c being 0 again. And then at 2 we have a plus 2b plus 4c being 1. So that is the system, and again the matrix of the bulk of it is an easy one, which starts as the linear problem system, and we have column of all ones, column of all x's, and then we'll have column of all x squares. These are the coefficients for the next unknown, for the new unknown c. So we'll have 1, we'll have 0, we'll have 1 again, and then we'll have 4. That is now our new matrix for the bulk, still calling it A. And the column B is the same column as we used to have. So we are solving now the system A times ABC, unknown column being equal to the same B. This is new A. Maybe calling it its width. And now, again, this system is unsolvable. You could quickly convince yourself that you don't have a perfect fit. So you don't have a quadratic function passing through the 4 points we have it. But we can do it in the least squares best way by solving the least square system for this one. So we have to multiply by the transpose of this new A matrix both sides of our system, and then solve this, and that will be solvable. So what is A transpose, 8 Whittle transpose times 8 Whittle? Let's just compute it quickly. As before, we are computing the symmetric 3 by 3 matrix with entries being scalar products of columns. And the first is, this entry is the scalar product of the first column with itself, which is 4. And the second is the scalar product. So this entry is the scalar product of this column and that column. We computed it before, it is 2. And in here, again, we computed it because we computed it in here, and all the products will be the same because that will be the scalar product of this with itself. And this with itself, or this with that, is the same answer, 6. Because in terms of our data, here we have just the sum of ones, here we have the sum of x's, here we have the sum of squares of x's. In the next line, it's easy to guess what we're going to have, the sum of cubes of x's. So that will be just the product of the two columns in here, and the sum of products, and will be -1, +1, and then 8. So there will be just 8. And finally, in this entry, we'll have the sum of 4 powers of x's. So it will be just squares of this column. Scalar product, scalar square of this column, scalar product of it with itself, which will be 1, 1 plus 16, and that is 18. And then on the right of the least square system for the quadratic fit, we will have to multiply our transpose of our 8 Whittle with this. And that is as before. The first entry will be the scalar product of all ones with this, so the sum of all the y entries, which was 3 and is still 3. The second is the scalar product of this with that, and that we computed before as well, it is 0. The last entry is the scalar product of this with that, and it will be 2, 0, 0, and 4, so that will be 6. So that is the system we have to solve now. And again, we could choose a better line that we have for the first pivot, say this one. Swap into rows, place it where it should be. and then start eliminating with it. So row 2 without twice, row 1 will eliminate this entry, row 3 without 3 copies of row 1 will make 0 here. Computing the rest. 2 without twice 6, that is -10. That is the computation we did before. And 6 without twice 8 is going to be -10 again. And then 3 is not changing in this computation. In here we have 8 without 3 copies of 6. So that will be 8 without am I doing it right? Yeah, 8 without 6 copies of 3 copies of 6 will be 18, so I'll have -10 again. And 18 without 3 copies of 8, which is 24. So negative, it's as if I'm subtracting 8 from 24, we have 6. And then 6 is not changing. And, well, doesn't matter which row I use for my second pivot, so that is good enough. I can simplify slightly the first row, but yeah, maybe just halving it is a good move. Doesn't cost much, doesn't affect the rest. And so these, keep it as it is, maybe changing the sign. But the third, row 3, is changed in this way to create the 0 below the second pivot, just subtracting. So we have a -6 and we're subtracting -10, we're adding 10, result is 4. We're subtracting out of 6, 3 in this position, so we're getting 3. Okay, elimination, and now in reverse above the last pivot. In row 1 we can just subtract row 3 from it and get 0 straight away, so we'll have -3 in here. In row 2, yeah, we can double it, so that will be 2 row 2 without row 3 5 times, and that will make 20 here, will make 0 here, and then -3 doubled will be -6, and then we are subtracting 5 copies of 3, so we're subtracting 15 out of -6, the result is -21. The final push is to get rid of this 3, so okay, doing again something clever, like taking row 1 and replacing it by 20 copies of row 1, and then subtracting 3 copies of row 2 out of it. And that will make 20 in this position, so that will become 0, it will become 0 as well. What is happening here is most interesting, so we have -60 and then subtracting out of -60, -63. So the result will be just +3. And that is effectively the answer for A and B and C. We can now write our quadratic function. So A will be 3 or 20. b will be negative 21 over 20, very close to 1. And then the c coefficient is 3 over 4. And again, it pays off to compute the values of this function at our data, at our x values for data set. So for x negative 1, we'll have 3 over 20. Maybe we could just try this as over 20 as well, so that will be 15 over 20, which will be easier for computations. So at negative 1, we'll have 3 plus 21 plus 15 all over 20. So that will be 24 and then 15 on top. That will be 39 over 20. And 39 over 20 is really pretty close to 2, so it's really indistinguishable from 2 with, say, this scale. It will be just below 2. At 0, this is just 3 over 20, which is pretty close to 0, but from above. Not as close as in here, but still close enough. At 1, we have 3 minus 21 plus 15. So it will be 18 minus 21. The difference between 21 and 18 is negative 3. Again, we are sort of the same distance away, but below now. And finally, the value at 2, so we'll have 3, negative 42, and then positive 60. It's 63 without 42. It is 21, which is again pretty close to 1. Really hard to see the difference. So plotting the curve, the quadratic curve, will have something like that. And this time the fit is really really good, so we can really see it arithmetically, computing again the deviation between the values we are given and then the values which this quadratic function takes. And this deviation between the 2 and 39 over 20 is just 1 over 20 squared. The deviation is 3 over 20 squared for the second data point, again for the third, and the last one is again 1 over 20. So we have twice over 400 the sum of 1 squared and 3 squared, which is 10. So what we have is over 200 or over 20. Well, yeah, we have 2. So that is really 1 over 10. I'm doing it right. 9 and 1 is 10. Yeah, so that is a much better deviation that we had before for the linear function. Not surprisingly, because now we can bend our curve really really close to the points we are given. And of course, if we continue to the next, would be cubic, but for the 4 points, there will be just the perfect fit will be unique cubic passing through 4 points. In general, if we have n points and we are allowed to use degree n minus 1, we can always find a perfect fit. But for least square and quadratic approximation, these are our answers. So we have them here for the quadratic, and for the linear one, we have it here. That is it. See you later.